Okay, so let's try another type of conical pendulum problem. I could ask you that a puck of mass 0.500 kilograms is attached to the end of a cord. The puck moves in a horizontal circle of radius 1.50 meters. If the cord can withstand a maximum tension of 50 newtons, what is the maximum speed at which the puck can move before the cord breaks? And let's assume that the string remains horizontal during the motion. Okay, so I have same thing, that conical pendulum, and in that conical pendulum, it's just going to be attached and I'm holding it, and that puck is going to move around and around in a horizontal circle, okay? I want to know and our tension will be directed up that way. I want to know what is the maximum speed that this puck can move in that horizontal circle before the tension, before that cord will break, okay? So if we think about this logically, if I have a really strong cord, so the more tension I have in this cord, that means that it's going to be able to withstand a higher speed. So a higher tension means that this puck can have a higher speed, okay? I could also think about if the mass of a puck was pretty large, so the more massive the puck, then that's going to mean the cord may break easier, right? Because if I have a bigger mass here, then it's going to have to, the bigger mass is going to pull on this more, so then that means it has a higher probability of breaking, okay? So a more massive puck, I'm going to have a lower speed. So I'm just thinking about these things logically right now. Okay, so what did I know and what did they give me? They gave me, if I go back here, I gave you a mass of 0.50 kilograms. Okay, so you're given a mass of 0.50 kilograms. We need to know V. I know the maximum, the tension that is in the rope when it could be at its maximum speed is 50 newtons. And they gave me that radius was 1.50 meters. So this is a little different from our last problem where we derived what we could use to find speed because we don't have theta. And I actually don't even need theta in this problem because I can think about it a different way. So really the force that's causing this puck to move in a circle is the tension. So I know centripetal force, or any force, is equal to mass times acceleration, but centripetal force is equal to mass times centripetal acceleration. I know centripetal force is equal to mass times v squared over r. I just plugged in v squared over r for AC. And the centripetal force that's causing this acceleration is tension. So centripetal force isn't just an extra force. It's a force that's already there. It's part of my free body diagram. So I have my tension force. I have my weight force. So it's a force that's already there. We just actually label which force is causing that acceleration toward the center of the circle. So really my centripetal force is tension. So tension equals mv squared over r. I know m, I want v, I know t, and I know r. So if I wanted to find v, it would be the square root of tr over m. So the tension force times the radius divided by then the mass. So if I do that and plug in my numbers, we said the maximum amount of tension was that 50 newtons before it would break. The radius was 1.50 meters. And I'm dividing that by the mass, which was 0.5 kilograms. So if I do that math, we should get V to equal 12.2. So this is just a different way to look at the conical pendulum. If I don't have an angle, if I don't have theta, I could think about what force is supplying the centripetal force. We know that that's tension, and I know that it's accelerating, so mass times acceleration, but centripetal acceleration is v squared over r. So if I know that tension is the centripetal force, I set those two equal to each other. I know all of these pieces, I'm trying to find this, so that situation worked out for us. Okay, so in general, if I'm thinking about a conical pendulum, as the tension increases, speed will also increase. So if I'm looking at this right here, so as tension increases, speed is also going to increase. But then as mass increases, so if I'm going back to the puck, if I have a puck that has a much larger mass, then the speed is going to decrease. Okay, we'll do a lab this coming week with the conical pendulum, so then that way you can see what that would look like. Okay, there's one more type of problem that I want to talk about, and that's called the flat curve. Okay, the flat curve, this is just kind of steps of like what we'll do when we're modeling a flat curve. So when you go around a curve in your car, you feel that force somewhere you feel being pulled in your hips, right? And we talked about this already, how there's a fictitious force, and then there's the actual centripetal force. And we'll get into those fictitious forces in this particular chapter. But a flat curve is where I have an object, specifically it'll probably be a car. The car is trying to maneuver around a curve, and what keeps the car in that circular motion is going to be friction, okay? The reason that, if you'll notice, this is labeled as F sub S, meaning it's static friction. The reason that this is static friction is because there's no slipping that is occurring at the point of contact between the road and between the tires. So because there's no slipping, that's why it's considered to be static friction. If there were slipping with it, it would be considered to be kinetic friction, okay? So if the static friction here were 0, then the car is going to continue to just go straight off of that flat curve, and then it would crash off of the road. Okay, so my goal is to figure out, I gave you this equation already, but let's prove how I got this equation. So on a flat curve, what we're going to do is model the particle in uniform circular motion. So I'm thinking about the particle as moving with mv squared over r. And it's going to move in a horizontal direction. I model the particle in equilibrium in the y direction, so some of the forces will be equal to 0. And then I think about the centripetal force is caused by the force of static friction. This is the maximum speed at which a car can negotiate or maneuver around a curve. V is equal to the square root of the static coefficient of static friction times acceleration due to gravity times the radius. How did I get that? So let's derive how I get that equation. Okay, my goal is to derive how I get V equals the square root of mu s g r. And this is for the maximum speed on the flat curve. Maximum speed for a flat